Today is Tuesday, April the 13th. Really? Tuesday the 13th? Today's the day we need to make sure we know how to do everything. Okay? So we're going to start off by going over the problems that we were doing right at the very end of class. We kind of ran out of time going over the answers of those 4 that we were working on. You have that whole worksheet. That worksheet has ideal gas law problems on it, just PV equals nRT. It's got stoichiometry at STP. It's got stoichiometry not at STP. Okay? And I think that's just, and then problems with the molar volume, the 22.4. I'm going to post tonight the answers to all of these. Okay, so you can practice and just kind of make sure that you know. Obviously, you don't have to do them all. We'll do some today, but just so you can look and do a practice 1 or 2 to make sure as you're studying for the test, which is on Thursday. Okay, test is on Thursday, so it's going to be. I mean, there's a lot of material on this test because we have all of our Q problems. Q equals MCAT, our heat of fusion, heat of vaporization, knowing those diagrams, and then doing the gas law problems themselves, and then gas law stoichiometry. So let's look at what we were just right at the very end of class, and I don't know if you guys had a chance to really see it all. And is it number 2 that you guys got 59.3?
Yes.
Yeah, I think I did it after you guys left and got 59.3 too, so. I think it's all set up right here. It's just supposed to be 59.3, not 5.93. This is the number 2. This is the bottom.
I got 59.5, yeah.
Yeah. And that's just going to be rounding. Where do you round? What did you use for the molar mass here? How much did you round off and all that? Notice on this one, you're given a gas not at STP, and you're asked to find how many grams of sulfuric acid reacts. So when you're given the gas initially, you got to do the ideal gas law first. That's your conversion to moles. So we converted here to moles. Then we used moles to go moles to mass.
That's STP, or no? That's a non-STP.
That's non-STP is when you have to use the ideal gas law. Now this one, you're given grams and you're asked to find the volume at non-standard conditions. So here you use the ideal gas law last. So you go mass to moles, and then plug that in because N is moles, not grams, and find the volume. So you just use the ideal gas law as the conversion factor. If it's at STP, what's the conversion factor?
22.4.
22.4, so it's going to work for all of them.
So number 1, when do you subtract the water pressure?
Right here. It's because it's collected by water displacement. So to get the pressure, you must subtract the water vapor pressure. Now again, there's a table in the back of your book where you get this. It's that R80 something, green pages. On a test, I'll just be given to you in the problem. Your clue, the words that tell you you need to do that is that gas is collected by water displacement. Okay? That's how you know that's what you need to do.
Is it always 23.8?
No. It depends upon the temperature. Water evaporates at different rates based on the temperature. But you'll always be given, you just look it up on the table, whatever temperature it is, you look up what the value is going to be on that. Okay? So, if I'll be able to stick that back up there. All right, so that's that one. You're supposed to kind of work on this one as well. So this one,
What was this one?
no, actually, this is the second 1 and 2. We haven't done that one yet, have we? And don't look.
We did 4 and 5.
Yeah, we did 4 and 5 on the other page. This one, is it the 12.5 liters of NH3? Now, this is the one where it was it K2SO4 or the other one. I found the K2SO4, isn't that the one it was asking for?
Well, we did potassium hydroxide.
But then you did the potassium hydroxide used versus potassium sulfate form because the problem was worded wrong. So what's the only thing that's going to be different if it's KOH?
We changed the grams on
Now is it 1 to 2 still here?
the,
No.
2 to 2.
2 to 2? So it's 2 moles of KOH for every 2 moles of NH3.
And then it's 56.11.
56.11. And then that comes out to equal
31.3.
31.3. Okay? So the setup's going to be all the same. It's just what are we looking for? Are we looking for the KOH? Or are we looking for the NH3? Let me move this down to just see the equation. It's 2 to 2 on this one. Now again, because it's at SDP, we get to use the 22.4. Yes, ma'am.
Why is the NH3 on the right, NH3 and it's NH4 on
Okay, because if you recall, one of our 3 types of double replacement reactions is called a gas-forming reaction. Okay? So whenever you're going to get potassium sulfate and then ammonium hydroxide. But ammonium hydroxide is unstable and always breaks down into NH3 gas and water. What's the other one that always broke down?
H2.
Okay, it makes CO2.
H2CO3.
H2CO3 will always make
Water.
H2O and CO2. Those are gas-forming reactions. You just have to recognize when that product is made, NH4OH or H2CO3, that it really is going to break up into the gas plus water. Okay? All right, so again, because of the wording of this problem, we chose to find out how much KOH was used, which is kind of the way the question asked. Really, it needed to say how much K2SO4 was produced. Okay, so if you wanted to find that one, you just do the 1 to 2 versus 2 to 2. Now the second part is how much ammonium sulfate was required. And now we just make this the X. Are we good with these? Anybody have anything that you're just not sure about? Okay, I'm going to move this up just so you can see the. Yes, ma'am.
I got a different molar mass.
For for which
The
side?
114.2, I had 132.17.
This one?
Yeah.
Did I really have a bad day? Let's just see.
I got 114.15.
0.5, I can deal with that, but this is going to be 18 times 2 is 36. 36 and 32 is equal to 68. 68 and 64 is equal to 132.
Yeah. That's right.
Yeah, that's what I got.
Hmm.
You forgot to do the NH.
I didn't do that twice
Times 2, yeah.
because I'm 18 short. I don't know when I did this, but obviously it wasn't a good time. I messed up twice.
I got the same thing at the 100.
Well, if you only did one NH4, if you didn't double, this is 14 and 4 is 18. Times 2 is 36. If you don't do the times 2, you get the 114. All right, so that means that this number is supposed to be 132 What decimal did you get?
1.7.
1.7, so 0.2. And then that makes that what?
6.64.
Okay, 6.64 grams, if you do it correctly. I think I did this during COVID. My brain was not in a good place. Gotta be some excuse for me to make all kinds of mistakes, right? Can't be just that I'm stupid. No. All right. Then, did we do this one as well? No?
That was the one, that was for the first one and two, I think.
Well, I thought that was,
We only did
no, that's
four.
number 6.
We only did 4 problems.
This is number 6.
Yeah, we only did
Oh, yeah, we
Yeah.
already did this.
Okay. So, we have ideal gas law, PV equals nRT. Then we have Boyle's, Charles, Gaylor-Sachs combined gas laws. Those are just kind of plug in. Most of those might probably be multiple choice. Okay? Because it's just P1 V1 equals P2 V2. You're given 3, having to find the 4th. It's just a simple math. Okay? PV equals nRT. You're going to know to use it when you have grams or moles and only one set of conditions. Then if you know it's stoichiometry when you have a chemical reaction involved. All the just gas laws is going to be a gas is in a balloon or a container at such and such temperature and pressure. How many grams will it be, or how many moles will it be? What volume will it occupy? But there's no chemical reaction. It's just one gas. Boyle's, Charles, Gaylor-Sachs combined, PV equals nRT. But when you have a chemical reaction, something's reacting with something. That's when you're going to know you're going to need to do the stoichiometry. Okay? When we do a gas volume to gas volume, what's the only step we have to do?
Mole ratio.
Mole ratio. Because volume and moles, proportional, they act in the same way. All right, get your study guide out that I gave to you. I have one up here. Okay, the first question on the study guide, I have one somewhere.
What is an ideal gas?
So the first question is, what is an ideal gas? Anyone know? What do you think? What is an ideal gas?
Yeah. It's like perfect, has like perfect, like,
Okay.
amounts of everything.
Everything's perfect. Okay, you know what the definition of an ideal gas is?
The ideal gas.
An imaginary gas. Okay? Now, this second part here, the two assumptions, is the rest of the definition. Okay? An ideal gas, two assumptions of an ideal gas that are not true for a real gas. Now, a real gas is just that: carbon dioxide, oxygen, nitrogen, helium, any gas is a real gas. Two assumptions. Number one, I'm actually just, rather than me writing it out, gas molecules exert no attractive forces on each other. Now, real gases do. We know that real gases do. We spend a lot of time talking about IMFs. But what do we know about those IMFs? Are they strong or weak? Weak. And they're only going to operate when the molecules are real close to one another. In a gas, are the molecules real close to one another? No. And they have enough energy that they're well above their boiling point. They have enough energy that where the attractive forces are really insignificant. So as long as the temperature is high enough and the molecules are spread out enough, the attractive forces are really negligible. Now, how many points can you put on a number line? Why? I know, but how can we fit, if you have just a line segment, you can still get infinite number of points on that line segment, right? Why? Because how much space does the point take up?
It can be small.
0, right? The point itself takes up no space. Scientists say that in an ideal gas, the gas molecules are infinitely small. They take up no space. The entire space of a gas, the entire volume of a gas is the space between the molecules. The molecules themselves don't affect the size. Now, when is that not going to be true? When is the size going to become a much greater factor? I didn't hear that. What? Bigger gases, possibly, but still, gas molecules are generally spread out pretty far where it doesn't matter how big or small. That's why equal volumes can contain the same number of molecules. But when is the size going to be an issue? When the molecules are close together or far apart? Close together, right? How do you get them close together? Increase the pressure, right? You compress them, you push them together. Okay? So gas molecules, the real gases do exert attractive forces, and they do have small but finite size. Under normal conditions, those two factors aren't an issue. But if I cool the molecules down, I slow them down, now the attractive forces are going to be more significant. If I push the molecules closer together, then the size becomes an issue, and the attractive forces are more significant because they're closer together now. What happens to a gas if you compress it and cool it? And eventually it what? Say what? Becomes a liquid. Do liquids obey gas laws? No. Okay? So the closer a gas is to becoming a liquid, the lower the temperature, the higher the pressure, the closer it is to becoming a liquid, the less ideally it's going to behave. In other words, when you plug it into P1V1 equals P2V2, what you predict by the equation and what is reality aren't going to be the same. Because in an ideal gas, if the pressure approaches infinity, what should the volume approach? 0. But eventually gas molecules are going to get in the way of one another and they can't go to a 0 volume. So the closer you get to being a liquid, the less ideally they're going to behave. They're going to deviate from ideal behavior. So that's this other question. Okay, under what conditions of temperature and pressure do real gases deviate the most from ideal gas behavior? Why and what happens to the gas? It's going to be at low temperature and high pressure. Because as the gases slow down, the IMFs have a greater effect. Now, I have issues. A lot of teachers and even books say that the IMFs are stronger at low temperatures. Well, the IMFs between water molecules, the IMFs between any gas molecules do not change. There's a certain London force based upon the size of the electron cloud. There's certain dipole-dipole attractions based on how polar it is. But as you cool them down, the attractive forces become more significant. It's like Elmer's glue on your hands. If you're moving your hands fast, the Elmer's glue is not going to make your hands stick together at all. But if you slow your hands down enough, that Elmer's glue then can start taking hold. The Elmer's glue didn't change how strong it was based upon how fast you move your hand. It's just when you're only putting a little bit of energy, the Elmer's glue now is more significant towards that energy. Same thing here. As the molecules slow down, the weak attractive forces now become more significant because the molecules are now going slow enough to where they can start taking hold. What temperature does water boil? 100 degrees Celsius. What temperature does steam condense?
What's-
Okay. 100 degrees. Remember the boiling point condensation. What temperature does water freeze? What temperature does ice melt? 0. Difference in potential energies, but kinetic energies are the same. Temperature remains constant during a phase change. So the boiling point and condensation point are the exact same temperature, it's just boiling going up, condensing coming down. Right? So the closer a gas is to becoming a liquid, the closer it is to its boiling point or its condensation temperature, the less ideally it behaves. And I think I said that.
Mr. Hobbs, what's the triple point for water? Or is there one?
There is, oh, there's definitely one. The triple, it's like 0.01 degrees Celsius, and the pressure is about 0.4 atmospheres, so near a complete vacuum. But then water can be a solid, liquid, and a gas all at the same time.
So we couldn't do that here.
We did.
Like we did with
Not
that,
water.
with the hexane,
But not water.
okay? Mr. Graber does a demo where he gets it with, for just a moment, 1 or 2 seconds with carbon dioxide. You can't hardly see it, it's hard to tell. Okay, this is the key statement right here. That's why it's all bold. And I'm gonna post this is what I'm gonna post Wednesday at 6. So you have to have your study guide done Wednesday at 6. Okay? But I'm giving you the first couple.
On the ones where it says it's rework the problems, we need to like write some of them down.
No, I mean,
Like,
no.
Oh, I just put a check mark on it, I was like, okay.
Yeah, but what you need to do as far as a study guide is you need to go back and work some of those.
Can we do number 6A and A?
On that worksheet or on
Or
the study guide?
On the study guide, cause, or like do one similar to it. Or wait, no,
Oh, yeah,
A,
yeah.
B,
Number 6?
yeah.
Okay. Well, just take a second right now and just see what you can do on it.
Oh, Mr. Hobbs, I did it like 6 times last night.
Okay, I know, but I'm gonna let everybody else have a chance, because they may have started working on it yet. Okay, so just a gas volume, this problem right here, 6A and B, should take you no more than like 2 to 3 minutes at the most. Really, I was gonna say like 30 seconds, but I was trying to be gentle.
Yeah, it was like midnight, so.
I know, I'm just telling you is that you're overthinking it, making it harder than it is. Yes, sir, Jackson.
So what was the bottom part of 7C? Mine was like,
It was like the whole thing.
It says in the following four, if the following 4 gases are put into, well, I don't think I can keep that one on there and get to that one. If the following 4 gases are put into a latex balloon, which will escape the tiny openings in the balloon the fastest?
C.
Chlorine at 70.9 grams per mole, CH4 at 16, argon at 40, or SO2 at 64.
CH4,
Why?
because it's the
It's
smallest,
the smallest. Which one's gonna be going the fastest?
the smallest one.
That's right. So which one's gonna be going the slowest?
The biggest one.
The biggest one. Super easy.
I wrote that down on here somewhere.
Okay, do you have it, Jackson?
yes, sir.
For 7B, that was my answer.
Do you have a big machine going back? I know that one. I play tennis, that makes fun of me all the time. I say, I run like a deer, a John Deere. All right, so you should be done. How do somebody help Clay out. If I'm given 5 liters of hydrogen, react with excess nitrogen, according to the following equation, how many Well, how many liters of NH3? Well, it's the mole ratio, right? So it's 5 liters of H2 times 2 NH3s for every 3 H2s. So you're gonna get 3 1/3, 3.33, right? So Clay, how many liters of nitrogen? If I have 5 liters, now I need to know how many liters of nitrogen.
You could just do one over 3.
1 over 3. So it's gonna be 5 liters times 1 N2 for every 3 H2, 1.67.
I wrote that down and then erased it because I don't know.
You're thinking, hey, this is too easy. This can't be chemistry. It's too
Yeah.
easy. I always tell people, I try to make chemistry hard, I just can't.
It was 12:04 this morning when I was doing it.
Maybe that's when I did the key. Maybe I stayed up too late when I did the key for that other one. That was my excuse. Okay? Gas volume, not at SDP, that's the ones we were just looking at. Gas volume at SDP, those are the ones we were just looking at, these two on that worksheet. Yes, sir?
What is partial pressure?
Okay, that's again, in this room, there's a mixture of nitrogen, oxygen, argon, carbon dioxide, and a bunch of other stuff, water vapor, okay? The total pressure is 1 atmosphere. But the partial pressure of nitrogen is what part of that 1 atmosphere is nitrogen exerted. The partial pressure of nitrogen, since nitrogen is 78% of the air molecules, that means that the partial pressure of nitrogen is going to be 0.78 atmospheres. The partial pressure of the oxygen is going to be 0.21 atmospheres. The part of the total pressure that's due to an individual gas. Dalton's law says what about the partial pressures?
They make up the total.
You add them together for the total pressure. The thing about gases is they act independently. If somehow I could suck all of the nitrogen out of this room, just nitrogen, and leave the other gases, is the oxygen just going to collect here in the middle? No, it's still going to occupy the whole space, right? Still going to be colliding with the walls the same number of times as if the nitrogen's here and nitrogen's not here. So the pressure of the oxygen's not going to change whether the oxygen's here, probably whether the nitrogen's here or it's not. Gases all act independently because there's no attractive forces, they're all spread out. So, they're just all just floating around doing their own thing. Yes, sir.
Okay, this is another easy one that I think was just.
That's all right.
17B, what phase will the substance be in at room temperature at 25 degrees Celsius?
This is on the study guide?
Yes, it's just the little phase diagram that I don't,
Where is,
I think that's just another one of those that was midnight.
It's at the very bottom.
I know, but it's not on the very bottom of this one.
It's just the
It says what
last.
phase.
I know, I see it, it's just, for some reason or other, I don't have, on the one I pulled out here, I don't have it. Let's see. I have the one with the answers on it, but I was gonna try not to. All right. All right, so define critical point. What is this critical point?
It's the point where it needs to be solid liquid
No, that's triple point.
It can be a water vapor and a liquid.
No,
Gas and liquid states of a substance become identical and form one phase.
okay? That's complicated. That's a
Yeah.
good, look up the answer.
2 phases.
It was
Okay.
in the book. That was what was in the book.
Substance that you can't-
I know, but I defined it in
Nope.
class. You were supposed to write notes down. Okay? The critical point, the critical temperature is the highest temperature in which a liquid can remain a liquid under any pressure. the highest temperature in which a liquid can remain a liquid under any pressure. I gotta put glasses on when I read this. Phase diagrams, 335 through 36. Okay, so here's the one in the book. So notice the temperature is 373.99 degrees Celsius. Water normally boils at 100. But remember, what's the definition of boiling?
When the vapor pressure equals atmospheric pressure.
Vapor pressure equals atmospheric pressure. So normal atmospheric pressure is here at 1. You heat up a gas, heat up water, it begins evaporating faster and faster. You have a greater and greater vapor pressure until finally the vapor pressure of the water equals normal atmospheric pressure. But then I brought the vacuum pump out and I lowered the pressure down and I made water boil at room temperature somewhere around in here. Because I just decreased the atmospheric pressure artificially. But if we use a pressure cooker, we don't let the steam escape, we can build the pressure up. And as we increase the pressure, what does that do to the boiling point? Makes it higher. So we keep adding pressure, we make the boiling point higher and higher and higher until, bam, there's a max. Now, in order to make water not turn into steam, not boil, at 373.99, you have to have at least 217.75 atmospheres of pressure. That's a lot of pressure. You go to 374.00, doesn't matter if you put 1,000,000 atmospheres, it's turning into a gas. Critical pressures, that's the minimum pressure that you have to have at the critical temperature to keep it from boiling. You can have more than that, but you have to have at least this much. But above that critical temperature, no matter how much pressure you put on it, it's going to turn into a gas. Now, the most important thing about that is the higher the critical temperature, the stronger the attractive forces. The longer it can stay a liquid means that they're stuck together pretty strongly. Now, notice on this one, this goes this way. On the one in your notes, which way does this line go? That way, right? Most substances go this way. In other words, you increase the pressure, you force the molecules together, they freeze. They form a solid easier because most substances contract when they freeze. Because water is one of those rare exceptions that it expands when it freezes, the pressure actually resists it from freezing rather than forming it. One day you guys are going to experience that soda thing that I was telling you about. Pull a soda out of the fridge, or if you put it in the freezer and forgot about it. It's not frozen. As soon as you open it up, it freezes and turns into a slush. The pressure keeps it from freezing. As soon as you take the pressure off, the molecules can expand, and they do, and they come out and they make a mess. You get Coke slushy. All right, these are good questions.
The place answer for, on B would be a solid.
Oh, yes. All right, so back to this then. What phase will the substance be in at 25? Well, let's just say, and I'm assuming, just assume atmospheric pressure here. So maybe write in add atmospheric pressure. Okay, so 25 is going to be like right here, right? If this is 0, well, 0.01, but close enough to 0, 100, that's about 1/4 of the way. So you just kind of, at 1 atmosphere, oh, we're right on the borderline, aren't we? No, 1 atmosphere is up here, okay? So I'm at 1 atmosphere right there,
Liquid.
so it's gonna be a liquid. It's in this liquid.
Not the arrow, 22.
I don't know why that arrow's there. I just picked that off the internet.
Looks like that's the answer.
Yeah, it does kind of point right to the answer on B. Okay? So then what happens, we just answered this, what happens to the boiling point is the pressure is increased. It increases. So as you change the pressure, you change the boiling point. So in the mountains, where the air pressure, is the air pressure greater or less in the mountains? Less, because there's less air above you, right? Because you're higher up. So what happens to the pressure, water, the boiling point of water in the mountains? It goes down, it's less. That's why food takes longer to cook, because the water's boiling, but it's only at 90 degrees rather than 100 degrees.
Because they're directly.
Okay? Anybody else been going through? Okay, but just take the last 10 minutes and just keep going through the study guide that you want, and if you have any questions, then we can answer them.
Is there a specific temperature we need to do for number 18? Like if the ice is at.
No, that's just, I mean, you just go back and look at the ones we did. I mean, I can give you a minus 20 degrees, ice to 150 degrees steam, or you just need to be able to go anywhere in between. You can go from water at 25 to make it, boil, become steam at 100, which would only be just 2 steps.
And that's heat of fusion and enthalpy and.
The heat of fusion is for freezing. The heat of vaporization is for boiling.
So don't we add all the MCATs and those? Are we
Yes.
nice to stay?
Yes, okay.
Do you be able to explain like the other 2 graphs we looked at?
The temperature graph,
There's the.
the Maxwell-Boltzmann temperature distribution graph was one of them, wasn't
Where's the one with the
Wait,
blue line and the red line?
it?
Kinetic
Yeah,
energy.
that's the Maxwell-Boltzmann
That's it? Okay.
temperature distribution
And then
graph.
There's
Yes.
another one.
The other one,
With the 3 lines.
Wait, the triple point is where.
That's all I got.
2 lines, 3 lines.
Not where the thing can be.
Or they all exist at the same time. Yeah. I didn't write this down somewhere. What's this
Okay.
one called again?
You calculate the energy.
You got 2 gases. They're at the, pardon me, here you got 1 gas. This is going to, I'm going to change it. You got 1 gas at 2 different temperatures. Remember, temperature is a measure of the average kinetic energy. If I fill this beaker up with water, all the molecules inside are not going the same speed. Some are going fast, some are going slow, but there's an average. They're bumping into it. I always think of like pool balls. When they bump into one another, one speeds up, the other slows down, constantly colliding with each other. But the kinetic molecular theory says that those collisions are perfectly elastic. No energy is lost. So one's going 5 miles an hour, one's going 20. They collide. One now might be going 15 and the other 10. But it's still going to add up to 25. Okay? You're not losing any energy. So they're constantly bumping in. One speeding up, one slowing down. But there's an average. So right here, where the peak is, that means the number of molecules, the area under this curve is the greatest, which means they have a kinetic energy somewhere around here. That's the average kinetic energy. Whereas this one now is moved to the right. We've heated it up. We've extended the range so the peak comes down a little bit, but my average now is going to be still right below the tallest part of the peak. So I've increased the average kinetic energy by increasing the temperature. The area under the curve tells the number of molecules at any given speed. You have a lot more fast ones at the higher temperature than you do at the lower temperature. You only have this many, like at this point right here, you only have this many fast molecules, whereas you have all of these fast molecules. Which is, again, remember, evaporation is the escape of the high-speed molecules from the surface. So at the higher temperature, you have more high-speed molecules at the surface, so it evaporates more quickly. I was playing tennis Saturday morning at the Y when it was pouring down rain. We had an indoor court, but it was leaking. We almost had to have our match rained out inside. Which, by the way, I taught at a school in Baton Rouge that was so old and janky that I was a volleyball coach, and we had our varsity girls match was rained out because the gym was leaking so bad. we had a big plastic tarp up underneath where the main hole is, and I called it the Depends for the gym, you know, because it was just collecting all the rainwater and it would just bow, but it rained so hard and leaked so bad that thing gave way, and we just.
That's almost redneck.
That was pretty good. And our gym in Baton Rouge, believe it or not, was not air conditioned. Imagine how hot that was. And to make things worse, just to tell you how you know, how good you have it here. That gym had a flat roof with skylights, and the way you shingle or whatever a flat roof is you put tar all down on it, and then you put kind of rocks and stuff on top. Well, that tar, when it gets hot, leaked all through the skylights, and so there was black tar all over our basketball court as well. So I'd come in with a scraper in August and have to scrape off a lot of it, but all of our volleyballs had black streaks all over it, and it was just nasty. Just nasty. Our cafeteria wasn't air conditioned either. The auditorium, cafeteria, and the gym weren't. And Baton Rouge is hot.
So say 100 degrees.
It was miserable. Okay. Your question.
Can we just do one of the like number 18?
Just the conversion one? Yeah.
Yes, because I feel like we haven't done one.
We haven't done one in a while, but we have done one.
Well, yeah.
Okay, now, because we only have 5 minutes left, you want me just to go ahead and kind of work through it real fast?
Yes.
Wait, did you post that slideshow that we went through?
Yes,
Did I post it? I did,
Yes.
didn't I?
yes.
Way back. And then I'm going to post all the answers to the study guide and all the answers to the worksheet.
Don't forget to post an assignment for the study guide, so we can turn it.
So
Oh, so yeah, somewhere to turn it in.
Yeah.
I always forget to do that part. Hey, when in doubt, you can always just email it to me. Then I'll say, oh wait, here's the assignment, resubmit it. How much energy, and rather than writing it all out, let's just go from ice at negative 20 degrees to steam at what temperature? Anything above 100, what do we want?
174.
106, 174, what's the?
106, because it's lower.
It doesn't
It
matter.
doesn't matter.
All right. So, if we look at our heating curve, okay, we're going to start here and we're going to end up somewhere up in here, right? So we have our Q of the ice, we have Q melt, we have Q of the water, Q boil, and then Q steam. Right? Remember, you don't do one big step, you got to do the segments. So my QT, my total, is going to equal, whenever there's a temperature change, what equation do we, and how much, let's just say 50 grams of ice. What equation do I use when we have a temperature change? MCAT. So it's going to be 50 grams times the specific heat of ice, doggone it. Do we have, anybody have that worksheet out where you can tell me the specific heat of ice?
2.108.
Joules per gram to degrees Celsius. And what's my temperature change going to be? Negative 20 to 0. So it's going to be 20 degrees. We're going up, so it's going to be 20 degrees. Plus 50 grams times my heat of fusion. Now that heat of fusion is going to be given to you as well. It's 334, right?
Yeah.
Plus the 50 grams times specific heat of water is 4.184. Times what's the change in temperature of the water going to be?
100.
100, because it's going from 0 all the way to 100. Plus the 50 grams times your heat of vaporization, 2264. Plus 50 grams times the specific heat of steam, which is 1.996. And what's my change in temperature going to be?
6.
It's just 6 degrees. It's going from 100, so it's times 6. Multiply all that out, add it up. Okay?